Hey, hello everyone. I'm Noah, and today I'm going to be talking a little bit about 3D printing and robotics. So, as a general overview, for those of you who are already familiar with 3D printing or additive manufacturing, I'll give a brief intro. For those of you who aren't, this will be very informative. And then we'll talk about how you can use a 3D printer and how it relates to robotics, what progress has been made in robotic 3D printers. And one interesting topic is 3D printing for large structures. More on that later. And how you personally might be able to use your own robot to 3D print something. So, a basic overview to 3D printing. There are different types of additive manufacturing, which is a fancy way of saying 3D printing. But today we're going to be focused on fused deposition modeling, or FDM. However, I encourage you all, if you're interested in 3D printing, to take a look at the different types of additive manufacturing. There's selective laser sintering. There are many, many different types. So check those out. But fused deposition modeling, the idea is you have some nozzle here on the left, and you have some filament, which is usually plastic or another type of polymer, and it's heated up and you deposit it onto this platform, and you can create a shape with it. If you've ever taken a tube of toothpaste and put the toothpaste on a toothbrush, that is a form of additive manufacturing. This is just a little bit more complicated. And when you have this 3-axis machine here, which may look familiar, the nozzle is attached to the center bed here, and you deposit the material onto this printer bed. Sometimes the bed moves, sometimes the nozzle moves, sometimes both move. But the idea is you're printing material on there, and you're creating a 3-dimensional shape. And this cute little video will show how to make this immense castle out of just that one nozzle, which, if you can picture a different type of manufacturing, say if you had a hammer and chisel and you tried to carve the shape out of stone, it would be really, really impractical, basically impossible for any machine to do this. So additive manufacturing is the only way, or the most practical way, to make most of these highly complicated 3D shapes. So you can see as it's going, it goes layer by layer from the bottom up. Some systems are top down, but FDM is bottom up, and it produces one layer at a time in a back and forth motion. And you can see the result is very, very high quality, high precision. The better printer will give you resolution of fractions of millimeters or sometimes micrometers. And you can see it's a very large structure. But you can see that that frame is as big a material as you can, or a big an object as you can print. If you want to print something bigger, you need to make a bigger printer, and we'll get into why that's a problem in a second. So how do you 3D print? If you wanted to 3D print something yourself, this is the general process. First, you start off with a CAD model, either in SolidWorks, Inventor, FreeCAD, or any of these CAD modeling softwares, which you might be familiar with. You export the file as an STL or a compatible file type, and you can research what that means later on, into some slicing software, either Slicer or Cura. MakerBot has their own software too. And what this does is it takes this 3D shape and it slices it from the bottom up into 2D shapes that the 3D printer can then use the nozzle to print the material in. So it prints one layer at a time into that 3D shape. The slicer, or the slicing software, exports what's known as G-code, which you may be familiar with. It's essentially how you code a tool path. Sometimes if you have a CNC or a milling machine, it uses G-code. It's just how to control the actual position of the nozzle when you're doing the printing. The G-code then gets exported into the printer. Usually the printer talks directly to Slicer, so you skip this step, but it's good to be familiar with it. And then once you have the G-code into the printer just moves on its own, and it could take a few minutes or a few hours or even a few days, depending on how big the printed object is. So that's a general overview. How does the actual machine compare if it's a robot? Desktop printers are pretty common. They go for between a few hundred or a few $1,000s if you want one of your own, or if you work with one at your job. They're good for most hobby uses, or if you have a lab, they're great for a lab. It's compatible with most available CAD-based slicing software, so Slicer, Cura, the ones I mentioned before. And there are plenty of different models available. You could pick the best one for your job. I mentioned the Precision. If you need a very high precision one, it'll be more expensive, but there are still plenty of options available. The robot arms are a bit more complicated. Why do we care about having a robot arm? You'll notice that this Lulzbot here can only print something which is maybe 1 foot by 1 foot by 1 foot, so 1 cubic foot. If you want to print something big like a house or a building, you need to have something which isn't this gantry style. Otherwise, your machine will be impractically large. So if you have a robot which can either move around or have a greater range of motion, you can print these very large structures. You do need to perform some inverse kinematics, and don't worry, that we'll get into what that means in a second, for the end effector control. So as opposed to moving this one nozzle in 3 dimensions XYZ, you need to be able to move the entire robot arm such that you then move the nozzle in that XYZ plane. So how do you move a robot arm to control the position of your nozzle? There aren't too many of these robot printers available for personal use or for private use. They're kind of expensive and they're a little bit restrictive because you need to have a basic understanding of how robots work, which the average person doesn't. So we'll get into how we fix that later on. But how can the robot 3D print? As I mentioned before, you just have this 3-axis motion, which is relatively simple. But now if you have a robot with multiple links or a robot arm structure, you need to be able to control the angle of each of these links. And you have different motors which can do that. And this is a problem called inverse kinematics, where if you have a given position or velocity of your end effector, the tip or the nozzle on the robot, you need to be able to calculate what is your angle Q1, 2, 3, 4, et cetera, however many joints you have for the robot. And that can be very complicated and very computationally expensive, depending on what it is you're printing. But it is possible. I won't get into too many details on how to do it. That's an entire lecture on its own, but suffice to say, it's you have some 3D position and also orientation, so 6 degrees of freedom for your end effector here, and you need to have the calculations for your joint angles here. So that's the basic overview of how it works for a robot arm. So what are some examples of robot 3D printers? Here you can see we have a couple of robots. I'll actually start playing the video here. So you can see this is a group out of Singapore. They have a couple of robots which print in concrete, and they are able to move around. They have a mobile base, and they can work in conjunction to print something which is really, really cool. Yeah, so they work together, and it's nicely sped up, and they start printing. You can see they work from the bottom up, just like a regular desktop 3D printer, and they print one layer at a time. And the video is going, but you can see that when they finish the first layer, they go on to the second layer, and they're working together, which is really nice. That's really complicated programming. But eventually, I'll just speed through the video here. I'll let it play out. It's only a few seconds. But you can see they're working nicely up one layer at a time.
And so cool.
Yeah, it's really cool. I found this video. I was like, oh, I'm definitely going to show this in the presentation. And those of you who may be watching this in the future and aren't familiar with what's called infill, you may be asking, why are there huge gaps in the structure? That's just a property of 3D printing, where if you were to print the entire structure as one rigid object, it may be expensive both for material and cost. So there's some structural analysis you can do where you only fill in a small percentage of the actual structure to increase the, I guess, strength to weight ratio. So now that they have this small slab created, they move away and they go back to where they were. And this is just a nice little test article. So you can see on the right here, we have the nozzle just as before. It just moves in 3 dimensions, but the robot arm itself moves that nozzle based on the controller and whatever code has been put into it. So this can print something on the order of about a couple of meters in a few minutes, which is really cool. But what if you want to print something really, really big, like say a house? Well, that's where you have to turn to something a bit more of an industrial size. You can have these large, almost crane-like robot arms. You can see it has this telescopic truss on the top. I couldn't find a good video for this, unfortunately, but you can search it on YouTube. Just search 3D printed house. There are so many videos on it online. And what this does is it essentially prints in a ring, and it can change the length based on the top bar here. And in that way, based on what you just saw, it can print this house around itself. And then you might ask, how do you get the robot out? I don't know. That's a secret. Well, you have to print a really big door or something. But essentially, it prints the house around itself, and that gets around the idea of, if you have a tiny printer, how do you print something big? So you just have a robot arm do it. And then I hear you wonder, well, what are some really cool applications? This is probably my favorite application for it. If you want to build a house or a habitat on the moon or on Mars, this is the way to do it. You don't have to take like big igloo-based space rocks and stack them on top of each other. You can do something a bit more sophisticated, where you take a robot and you take the regolith or the soil, which is already on the moon or on Mars, and you use that as your 3D print feedstock. So instead of the filament, you use that, and you use that to print the habitat from the base up. So you don't need to haul any of this construction material. You can just do it on the surface, which is really cool. I'm not going to get too far into this, even though I already have, but I encourage you all to watch the videos on this or to look it up in your own free time. The product on the right here is called Marcia, which was pretty recent, a concept for 3D printing a base on Mars, and there's an equivalent for on the moon on the left, but it's the same idea. Yeah, so how can we personally do this? It's complicated. You'll see on the left, these are a few, there are plenty of other options, but these are a few options of the market printers that you could buy for yourself. They do range from a couple hundred to a couple $1,000s, depending on how invested you want to get into this hobby, if it is indeed a hobby. If you have one at your lab or at your job, you could probably play around with it just to learn more. But if you want to get a robot to do like a robot arm to do this for you, that's where it gets a little more expensive. This is one of the only quote affordable ones I could find, and it's about $1,000, which, yeah, that's a lot for a piece of plastic which can do some printing. But it is really cool. Once it drops in price, I might pick one up just because it's, if nothing else, a really fancy desk accessory. Just like, oh, this is a casual robot that I can 3D print stuff with. That's nice to have. But again, I encourage you to, if you find a more affordable 3D printer robot that you would want to get for yourself, I encourage you to do so, and please tell me about it because I would like to have one too. So that is all I have for today. If we have any questions, let me know. These are a couple references that you can always look up on your free time, or if you want to do some of your own research, feel free to do so. But I hope that was informative, and now I will take any questions you have.
This was so cool. I'm also just like with the big concrete ones, that would also significantly speed up printing time if you could have multiple of these working together. Because like if it takes you days, just get 10 of them, and then it takes you, like an hour.
Yeah, that would be the goal. The question then is, how expensive does it get to have 10 robots? Because I'm assuming, I didn't check the cost on the robot, but I assume it's pretty expensive. So if you have an army of these,
if you can even buy these at this point.
Yeah, I definitely would not be able to afford this. This is like, at this point, if you're a major construction company, sure, you could probably buy one. But again, it's also possible. Like if I'm talking in the future to a company right now, I could teach, like all I presented today is how you build one of these. You just need to know what is the inverse kinematics of your system, what do you need to print, so the actual motion of this printer, and then actually own the robot. And you could probably build one. If you already have a robot, you just strap a nozzle to it like they have here. You have an existing robot, you strap a nozzle to it, and then you have whatever material it is fed into the nozzle.
And then you just tell the robot where to go, as you normally would, and then you're done.
Yeah.
So I'm hearing is, this sounds like a very doable DIY project. Make our own 3D printer arm.
I think so. If a group of students wanted to get together and build one of these, is probably doable.
Senior design project.
It is a senior design project. You could very easily build one of these yourself. All you need is like an off-the-shelf 3D print, or off-the-shelf arm, which you can 3D print the parts for. There are plenty of robot arms this size that fit on your desk, which you can 3D print. And you could buy some kind of a material extruder, or you could get like a syringe and then use the syringe as a pseudo nozzle type thing, and you could make your own 3D printing robot arm.
My brain immediately went to just replace it with a bubble wand. Perfect.
Yeah, you could do that.
Not useful, obviously, but
it's a cool concept, if nothing else.
It's a good stand-in for if we all go, well, where do I get a nozzle? A 3D printing nozzle, yeah.
Yeah.
Anyway, cool. Thanks for this.
Sure.